The next exponential function, just like pi is an irrational number, it's a number that never repeats, nor terminates. We use 3.14. Anytime we see pi, we say, well, pi is roughly 3.14. That's kind of the habit. We have another letter. It's called E. E is the natural exponential base. E is 2.7182818284559. It's a number that's irrational, just like pi. It never repeats, it never terminates. We say e to the 1 is roughly 2.7, and that's all that matters. So our calculator, we have that key. We're going to use that today. I'll show you how that works. But if I'm ever thinking about what E is, 2.7 will do to get an idea of how things work. Which means, if I wanted to sketch the graph of y equal e to the x, since the base is bigger than 1, it's exponential growth. It crosses at the point 0, 1, and the asymptote is y equals 0. So, sketch the graph of the following: 2.7 to the 1, 2.7 to the x plus 2. Well, that is that graph. The point 0, 1 will shift 2 units up. It'll be 0, 3. Make sure you label that clearly. And the asymptote y equals 0, if I shift that 2 units up, that would be y equal 2. And the shape is exponential growth, and there it is. Done. That's all we have to do. Domain for those is always all real numbers. Always. The range, however, do you see that there's an asymptote? It's from the asymptote all the way up to infinity. What if I multiply the x by a negative? Multiplying the x by a negative reflect this graph with respect to the y-axis, because if you say y equal e to the negative x, that's really y equal 1 over e to the x. 1 divided by 2.7 is less than 1, so this is exponential decay. This graph looks like this. If I add 3 to it, the line y equals 0 will shift 3 units up. The point 0, 1 will shift 3 units up, be 0, 4, and exponential decay. And there's the graph. You want to pick points, you're welcome to, but this is all we need. And we could identify domain and range. How about here? Well, e to the x is right there. Multiplying the y by a negative. So e to the x, negative e to the negative x, negative e to the positive x. Multiplying the x by a negative, reflect this graph with respect to the x-axis. So this graph will flip, and it would look like this. And the negative 2 will take the asymptote and shift that 2 units down. And the point 0, negative 1 will shift 2 units down. That will be 0, negative 3. And the shape will look like this. It is crucial that you sketch a graph of any of these functions with ease. That's why I'm covering all the bases. How about here? Well, e to the x, one of those, passes through the point 0, 1, y equals 0. Multiply the y by a 2. That point becomes 0, 2. And this point will shift it 1 unit down. Multiplying y equals 0. So y equal, maybe I should do this, e to the 2e to the 2x will look identical to this. The negative 1 will shift the graph 1 unit down. Y equals 0 shifted 1 unit down will be y equal negative 1. And the point 0, 2 shifted 1 unit down will be 0, 1. Oops. And I'm looking at an exponential growth. So if you marked it like I did, you don't have to really tell me what that is. I provide the grid on the exam, so all what you have to do is make sure that if you scale it differently, you have to tell me. Otherwise, just mark it right on the point. Or if you want to be certain, just label it. How about this? Well, e to the x looks like this. Y equals 0 and the point 0, 1. This is going to shift the graph 1 unit to the left. You know what? This one I'm not going to rescale. I'm going to make each unit 1. So 0, 1. It's going to take this 1 unit to the left, 1 unit up. So if I label it that way, again, I don't have to put anything. And the line y equals 0, if I shift it to the left, it stays y equals 0. Shift it up 1 unit, it's really y equal 1. And the shape remains the same. So I need to track 3 things. The shape has to match, whether it's growing or decaying. That original y-intercept, not where this graph crosses the y-axis, we don't care about that. And the asymptote. And pretty much that's all there is to it. How about this graph? Well, let's see. If I start with e to the x is one of those. Multiply the x by a negative. Reflect this graph with respect to the y-axis. Now it's exponential decay. This is e to the negative x. Negative e to the negative x. Multiplying the y by a negative. Reflect this graph with respect to the x-axis. That point now is 0, negative 1. And the 3 will shift the whole graph 3 units up. So the line y equals 0 will shift 1, 2, 3 units up. The point 0, negative 1 will shift 3 units up. And the shape is identical to this. Here, the domain will be all real numbers. It's always all real numbers. But the range, do you see that? It's going to run all the way down to negative infinity, as high as 3, but never reaching. A radioactive substance decays in such a way that the amount of mass remaining after t days, so t is the number of days, is given by this function where n is the measure in kilograms. Kilograms. Find the mass at t equals 0. Well, if I set t equal to 0, put a 0 there, n would be 10 times e to the negative 0.012 times 0. That is 10 times e to the 0, but e to the 0 is 1, so it's 10 kilograms. Or if you look back at our original definition, not here, apologies, here. Do you remember that we said this was the initial amount? You could just pick it up, or you could just, if you want, plug in 0. 10 kilograms is what I'm starting with. Very good. How many kilograms remain after 20 years? So if t after 20 days. So what is, and this is pretty much is n of 0. N of 20. 20 days from now, we're going to have 10 e to the negative 0.012 times 10. N would be how many kilograms? Get my calculator out. And if I take 10 e to the negative, this negative, 0.012 times 20. Oh, I put 10. I'm going to fix that. Times 20. And what are we getting? 7.866. 3 decimals will do. 7.866 kilograms. We have a formula for continuous compounded interest or population. Either way. So, A equal P e to the RT. P is the amount that you start with, kind of like the deposit if we're talking about financially, putting money in a bank, that's a deposit. If it's a population, That's the amount of population that you start with. A is the amount after a given time. If we're talking about money, that's the balance in the bank account. Or that's how many are left, how many people are left after some time have lapsed, after some time. T is the number of years. They could alter that, but generally speaking, if you're dealing with compounded interest and, depositing money and all of that, it is the number of years. And R is the interest rate in decimals if we're talking about money. But if not, that's the rate of growth or rate of decay. If this is a word problem, this could not be in years. It could be in anything that they want it to be. But since we're going to focus on specifically one application in this case, and that is investment, T is in number of years. If $2,700 is invested, well, that's the amount I started with. That's the initial, like the deposit. At an interest rate of 4.77%. In decimal, that's 0.0477. So maybe I should put that right here. So for this problem, P is $2,700. The rate is 4.77%, which is 0.0477. Compounded continuously, that means I could use this formula. Most students call it APERT. Whatever works. Find the balance, find what A is after certain years, and let's see how this works. So this is me using my calculator. In part A, the amount left is 2,700, so I'm plugging those in. E to the 0.0477. In part A, I want T to be 2. And the balance will be, and again, not much to do. 2 years from now, if I deposit $2,700 in a bank paying 4.77%, in 2 year time, the $2,700 will grow to $2,970.27. If we're dealing with money, we round to the nearest penny. If we're dealing with people, we round to the nearest, or animals or anything alive, we round to the nearest integer. So 2971, 2970, and how many pennies? And 27 cents. So pretty much I made over the 2 year period a total of $270. What if I leave the money in for 5 years? What would change? 2,700, the same formula, nothing changes. The only thing that's going to change this will be a 5. If I have a scientific calculator, then all what I have to do is go back, and delete that and put a 5 instead. There it is. $3,427, $3,427 and 29 cents. So here I made a bit more. I made $727 and 29 cents. And how about if I left the money in for 7 years? Well, guess what? And that's pretty much all there is. The bigger question is, in how many years would the $2,700 become, say, $5,000? I need logs for that. That's where the next section comes in. And what am I going to do here? I'm going to go back again, my arrow, and delete that, and instead put a 7 years, and that's $3,770, $3,770 and 29 cents. And that's pretty much it for this section.